Hey guys, Ms. Gosling here. In this video, you're going to learn about work. By the end of the video, you'll be able to define and solve problems involving work. Now to clarify, when I'm talking about work, I don't mean homework or going to a job where you get a paycheck and all that fun stuff. What I'm talking about is the physics definition of work. So in physics, we define work, which we're going to measure in joules. That's a J, or in Newton meters. Both are acceptable for units for work. We're going to define work as the force required to move an object a certain distance. That is, it is going to be equal to the force applied parallel to an object times the distance that the object moves. The distance that force is applied over. So for example, think about pushing a box 10 meters. Now, if we have a non-angled force, so if I'm lifting something straight up, if I'm pushing it straight to the side, then my work is just equal to my force times my distance. However, if I have an angled force at an angle theta, then I need to multiply force and distance times the angle between the force and that distance that it moves. So think about with this, if I'm pulling a box at an angle, for example, think about pulling a child in a wagon. I have to take into account the fact that not all of my force is actually doing work on the wagon. So the force that's pulling up isn't doing any work because the object's not moving up or down. But the force pulling, the component of my force pointing to the side, horizontal, is going to be doing work. So let's go ahead and I think that work is kind of best understood through example problems. So we're going to be mostly focusing on those in this video. However, before I do an example problem, I do want to give, I think, two helpful examples for what work is. So say I have a box. Say I have a box on the ground over here. And my box is 10 meters away from my table. If I lift up my box and carry it to the table, the only work that I'm doing is actually going to be the work required to lift it up the height of the table. So the whole 10 meters doesn't require any more work to carry the box horizontally 10 meters than it does to move the box horizontally 5 meters. Because the only point where I'm doing work on the box is when I'm resisting that gravitational force and moving up. Similarly, if I push on a wall with a force, no matter how big that force is, I am not going to do any work unless the wall moves. Because again, unless I actually change the motion of an object, I'm not going to do any work on this wall. So those are kind of two examples of that relationship between the importance of our work being parallel to our force being parallel to the distance moved. So if I'm lifting my box up and then carrying it over, the only force that I'm applying is the force required to lift it. So that's the only point where I'm doing work. Similarly, again, if I'm pushing on a wall, unless that wall moves some distance, which I don't think it will, I'm not going to be able to do any work on that object. So here's a really simple example. You lift a box that is 5 kilograms up 100 meters. How much work did you do? So let's go ahead, and you'll notice I started by drawing a labeled picture with my box and the motion that it has. And I did that before I started writing my givens, and that's something I recommend many of you do. Pictures can often help clarify what the word problem is telling you. So let's talk givens. First, I know that the mass of my box is 5 kilograms, and I know that the distance that I'm lifting it up is 100 meters. Finally, if I were to draw a free body diagram of the box, I would know that the box has a gravitational force of mass times gravity, and that the force that I'm using must be opposing that force. So my applied force must be equal to my gravitational force. And that's because that's the only way for me to lift the box up at presumably a constant velocity, which I'll assume because the box doesn't say that I'm not lifting it at a constant velocity. So the last thing I'm going to need here is that little g is 9.8 meters per second squared. And excuse me, I should be putting a little negative sign here, right? Got to make sure I'm being careful with my directions. So my applied force is the negative of my gravitational force, right? Same magnitude, opposite directions. Similarly, little g, always negative because gravitational force pointing down. So now let's talk unknowns. And my unknown is, of course, what the question is asking me. And that is, how much work did I do? So my work is that. Now, I know that my equation for work here is going to be work is equal to force times distance, because all of the force that I'm applying is in the same dimension. It's all parallel to the distance that my object moves. Therefore, work is equal to my applied force times the height that I go up, or negative mg times the distance. Now that I have simplified my equation to only include my givens and unknown, I can start to sub and solve. So I know that work is equal to negative mg. So plugging in my numbers, my work is equal to negative 5 times negative 9.8 times 100. And when I multiply that out, I'll find that my work done is 4,900 joules, or 4.9 kilojoules. And there you go, guys. I have calculated for work. Now, one thing I want to mention is just like energy, work is a scalar. So I don't have to worry about the direction that the work is going in. It's either, so my work can be positive or negative. And we'll talk in the next video about what the difference is between positive and negative work. But what it does not indicate is the direction that the work is going in. So if I pull to the left or if I pull to the right, the work done is going to be the same. So let's go ahead and talk about a slightly more complicated example. You use a rope to pull your sister on a sled. You apply a force of 50 newtons at an angle of 30 degrees to the horizontal, causing her to move 10 meters. How much work did you do? So let's draw a picture. Here is my sled, and here is my sister sitting on that sled. I pull her with a force of 50 newtons at an angle of 30 degrees. And I pull her that distance for 10 meters. So let's figure out how much work I did. So my givens are my applied force, which is 50 newtons, the angle theta between my force and my displacement, which is 90 degrees, and the displacement of my sister, which is going to be 10 meters. My unknown is work, because that is, of course, what the question is asking me to find. And as always, and so now instead of using the nice, simple work is equal to force times distance, I have to keep in mind that the only part of my force that matters is the force that's parallel to my displacement, and add in that cosine of theta. And we can see here that cosine comes from the fact that we only care about the side adjacent to our angle, the side of our force in that horizontal direction. So moving forward, I can go ahead and move into the sub and solve stage and plug in my numbers. So I know work is equal to force times displacement times the cosine of theta, or 50 times 10 times the cosine of 50. Or excuse me, times the cosine of 30. I don't know why I wrote 90 here, but the cosine of 30. Can't read my own handwriting. There we go. And I can plug that into my calculator. And when I do that, I'll get that my work is 433 joules. And there you go. That is the work required to move my sister 10 meters. Finally, I want to give a third example, this one using graphs. In this example, we're going to figure out how much work is required to move the object 30 meters. And to do this, what we're going to look at is our equation. Force times distance is equal to work. So we know that the area of a rectangle here is given by base times height. And in this case, our base is displacement and our height is force. Therefore, the area under my graph is equal to work. And I'm going to write that in all caps and in all red. The area of a force versus displacement curve, and I say curve, by curve I mean line, any shape really. I like to use the word curve because it's a little bit more general. So the area of a force versus displacement curve, or perhaps a little more accurately, the area under a force versus displacement curve is the work done. So my question is asking me how much work was required to move the object 30 meters. In other words, what is the area under the graph from 0 to 30? So I'm sure you guys remember how to solve, it's been a while since you've had to solve graph problems, but you guys are going to pretty easily remember the trick. First thing, of course, split your curve up into shapes that you can easily find the area of. So I drew a line here because it is easy to find the area of a rectangle and it's easy to find the area of a triangle. I'm going to call this the area of my rectangle A1, and I'm going to call the area of my triangle A2. So my work is equal to A1 plus A2. A1 is equal to the base of A1, which is going to be 20 meters, times the height, which is 100 newtons. Therefore, A1 is 2,000 newtons. A2, on the other hand, is a triangle. So A2 is going to equal 1/2 times base times height, or 1/2 times my base, which is from 20 to 30, and therefore is equal to 10, times my height, which is this side here, so it's still going to be 100. Therefore, my second area is equal to 500. So my work done is equal to A1 plus A2, or 2,000 plus 500, or 2,500 joules. Got to remember our units here. And there you have it, guys. That is the work required to move my object 30 meters. Again, I just found the area under my graph. So let's talk takeaways. First of all, work is force times distance. And we can use the equations work equals force times distance and work equals force times displacement cosine theta to solve problems. Finally, we can find work done by finding the area under the curve in a force versus displacement graph. And I'm going to actually cross off the word distance and write the word displacement. I've been using both, which I should not be doing. I've been using them interchangeably. We only care about how far we are from our starting point. We don't care about path for work. So the correct term here is displacement. I know I use distance a lot in the video. So just a reminder, remember that distance, it's often not going to matter, but just so you guys are all aware, the correct term here is displacement, and we do want to think about how, we only care about how far we are from where we started. So there you have it, guys. You now have had your introduction to work. It's now your turn to solve some problems. Best of luck and happy solving.